Before the night grows quiet, picture a red supergiant hanging in deep space. Its surface is not smooth or still. Vast convection cells rise and sink, shaping bright patches and darker lanes. From that restless glow, dusty winds drift outward and carry away the star's outer layers. This is the slow road toward a supernova told gently and clearly. If this kind of cosmic sleep science is what you want more of, please like the video, subscribe and turn on notifications. In the deep red glow of a swollen star, the surface never truly settles. A red supergiant is shaped by giant convection cells that texture its skin. They help launch dusty winds and set the conditions for a later supernova. A broad disk hangs in darkness like a cooled ember behind a thin veil. Bright regions drift across it. Dark seams open and narrow. The light changes without hurry. The first unlock is clear within that calm variability. The surface is not a smooth shell, it is a moving pattern made by heat trying to escape through a deep, slow atmosphere. A close look would show mottled patches with soft edges. The mottling is not decoration, it is the visible footprint of the motion below. One scene holds steady in the mind. A faintly swollen limb fades into a halo where the disk seems to blur. That blur is not an error. It is a physical gradient where light emerges from cooler layers farther out. Convection is the engine under the mottling. Warm gas rises, cooler gas sinks. On a red supergiant, the cells can be so large that only a few dominate the visible face at once. The second unlock follows at once. If only a handful of cells rule the surface, then small changes in their position can change the whole star's brightness. The pattern behaves like weather, yet it moves on enormous scales. A bright region is not a flame, it is a slightly warmer patch in a generally cool photosphere. A dark seam is not a crack, it is cooler gas where molecules absorb more of the outgoing light. The physical detail matters. Those seams often trace curved lanes. They mark boundaries where flow turns and sinks. The mind can hold an everyday analogy without pulling in anything human. Warm air rises over a sunlit plain. It forms broad updrafts and slower sinking zones. Now the scale shift arrives gently. Those familiar cells are measured in meters and kilometers. Here, a single cell can span hundreds of millions of kilometers. The difference is not just size. It changes the rhythm of change. Flows that would look fast on a small world become slow when the distance is vast. Another visual anchor returns. Across the disk, a brighter patch swells and thins like a cloud deck seen from far above. A darker lane slides along its edge. The third unlock sits inside that image. Even without a strict pulse, the star can appear to vary because the surface is rearranging its own brightness map. The edge of the disk refuses to be sharp. At this distance, light behaves as a layered leak rather than a clean boundary. The limb grows dim through a smooth gradient. The gradient exists because the line of sight grazes cooler, higher layers. A radius defined by one color of light will not perfectly match a radius defined by another. This is not a contradiction. It is a reminder that the outer star is thick and extended. A calm payoff follows. If the edge is a gradient, then the atmosphere is part of the star's visible body. It is not a separate wrapper. The main number can hold that here. The radius can be about 1,000 times the sun's radius. In a size analogy, a pebble becomes a small mountain. That scale sets a quiet consequence. Surface gravity is gentle. Gas does not need to race away in a single leap. It can be lifted in stages. Convection and slow heaving motions can push material outward until it cools enough at a change phase. Another anchor scene forms just above the limb. A thin veil thickens into a faint envelope. It looks uneven. One side seems slightly brighter and more extended. That asymmetry is a clue. The wind does not start everywhere the same way. Now a second core concept enters and stays. Dust forms in the cooling outflow. Dust is made of tiny solid grains. Grains form when atoms stick together in cooler, denser gas. Two examples ground the idea without crowding terms. Fine sand can appear in air after a dry gust. Salt crystals can appear as water slowly leaves a shallow pool. Why it matters becomes the next unlock. Once grains exist, light can push on them more effectively than on thin gas. The grains feel a gentle outward shove from starlight. They drag surrounding gas along through collisions. The wind becomes easier to sustain. A new visual anchor settles in. Outside the star, faint arcs drift outward like slow ripples in fog. Some arcs look denser, some look thin. The motion is not seen as a blur. It is inferred as structure that changes position over time. Here the limit of observation arrives softly and precisely. A signal would merge layers along the line of sight. Brightness is an average through depth. Surface features cannot be read as if they sit on a single flat skin. A dark seam might be partly in front of a brighter region. A brighter region might be veiled by cooler gas above it. The limitation is the loss of depth information in a thick atmosphere. Even perfect sharpness across the disk would not reveal the full three-dimensional flow. That limit does not end the story. It shapes how the story is told. Patterns at the limb become evidence of height. Changes in the halo become evidence of outflow. Another payoff follows. If the outer layers are hard to separate, then the wind itself becomes a record of the surface that launched it. The scene widens to the space around the star. Knots and wisps curve outward. The envelope looks like layered mist that carries faint rings. Each ring is a physical detail, a denser shell where outflow briefly strengthened. The analogy can stay natural. Cloud layers after a long night can preserve bands of humidity. The bands drift and spread. So do these shells, only on grander distances. A final scale shift closes the opening arc. Minutes and hours describe the motion of a single patch on the surface. Years and decades describe the building of a dusty envelope. Centuries and longer describe the interior changes that approach collapse. The calm promise is set without suspense. These first surface patterns connect to deeper layers and longer clocks. The next section moves inward to the slow physics that make such giant cells possible. A red supergiant surface looks calm from afar, yet the calm is built from slow upheaval. Giant convection cells dominate the visible face because the outer layers are thick, cool, and easy to stir. The first unlock is simple. The same process that carries heat upward also sculpts the star's brightness into a small set of moving regions. One scene holds steady as a primary anchor. A broad, bright dome swells near the center of the disk. A darker trench curves around part of its edge. The trench is not a crack. It is a lane of cooler sinking gas where light escapes from slightly deeper layers. The dome is not a flare. It is warmer gas rising and thinning as it reaches the surface. Convection is the first core concept, and it stays. Convection is heat carried by moving material. Warm gas rises because it is less dense. Cooler gas sinks because it is denser. Two familiar images help without pulling in any human world. In a shallow hot spring, clear plumes rise and spread. Cooler water sinks in slow curtains along the sides. In a fog bank over cold ground, some parts lift and thin. Other parts collapse and thicken into darker bands. Why it matters becomes the next unlock. When the motions of that large brightness changes can come from rearrangement alone. The star does not need to erupt to vary. It needs only to shift which upwellings face outward most directly. The second core concept enters with a short definition and then returns to plain language. Opacity is how strongly material blocks light. When opacity is high, light is trapped longer. When opacity is lower, light slips out more easily. In a red supergiant, opacity changes rapidly with temperature and density. That creates a feedback that makes the surface more patchy. A rising region becomes a little warmer. Opacity drops a little. Light escapes more easily. The region appears brighter. Nearby sinking gas cools. Opacity increases. Light struggles more. The lane appears darker. A small payoff follows. Bright and dark patterns are not painted on top of a steady star. They are the star's heat flow made visible. Another visual anchor arrives at a slower pace. The limb is not a clean circle. It is a soft gradient where brightness fades over a wide rim. The gradient thickens on one side, it thins on the other. That asymmetry hints at height differences in the outer layers. At this distance, light behaves as if it comes from many depths at once. The eye would prefer a single surface. The star offers a stack of semi-transparent layers instead. The limit of observation appears gently and clearly. The main limitation is depth confusion in a thick atmosphere. A signal would blend together features from different heights. A dark lane can be partly a shadow of cooler gas above. A bright dome can be veiled by the thin haze that is nearly invisible elsewhere. Even a perfect image cannot separate those layers cleanly. The inference is indirect. Patterns are mapped in brightness, then translated into motion by models. That translation is powerful, yet it carries uncertainty. Another unlock follows from that limit. The best clues come from change over time, not from one frozen view. If a bright dome drifts and reshapes the motion suggests a flow. If a lane widens and then pinches off the change suggests sinking and spreading. The primary number can now enter safely and carry an everyday comparison. A single convection cell can cover about 1/4 of the visible disk. That is like one cloud covering 1/4 of a sky dome. The scale shift lands softly. In small settings, convection breaks into countless tiny cells. Here the count is low. The surface becomes a map with only a few dominant regions. Another visual anchor forms in the mind as a slow sequence. The bright dome stretches into an arc. The arc breaks into 2 islands of light. Between them, a dark seam grows into a curved band. The band thickens like a slow-moving shadow on a soft wall. The next payoff arrives. The pattern is not random speckle. It has coherence because the cells are enormous and slow to overturn. The star behaves like a deep fluid layer that prefers broad structures. The analogy remains natural and unique. Over a wide desert after sunset, heat can linger in broad layers. Warm pockets drift and flatten. Cooler pockets sink and spread. The same idea scales upward. The difference is that the red supergiant's outer layers are vast. Their gentle gravity allows large motions to persist. Physical detail keeps the picture grounded. Where gas rises, it expands and cools. The cooling can allow molecules to survive. Those molecules absorb light in bands and deepen the contrast. Where gas sinks, it compresses and warms. The warming changes which wavelengths escape more easily. The surface becomes a shifting mosaic made from temperature gradients and opacity gradients. Another visual anchor appears closer to the rim. Thin filaments extend outward for a short distance. They look like faint streamers that blur into the halo. They are not jets. They are uneven extensions of the atmosphere where rising flows lift material higher than nearby regions. A small payoff follows at once. The same cells that shape brightness can also lift mass upward. Lifting does not mean escape yet. It means gas reaches cooler heights where new physics becomes possible. The story now takes a gentle step outward without leaving the surface behind. A lifted parcel cools. Cooling increases the chance that atoms stick together. That sets the stage for dust grains later. The third core concept stays implicit to avoid crowding terms. The idea is a threshold in temperature and density. Above the threshold, gas remains transparent enough that light passes through. Below it, solids can begin to form and light can push more effectively. Another limit of intuition slips in without strain. A mind expects wind to be driven by a single steady push. Here the push can be patchy. It can begin in one lifted region and fade in another. The surface patterns matter because they set the starting conditions. A final visual anchor steadies the closing. The bright dome near the centre dims slightly. The dark trench softens and breaks. The limb halo thickens for a time, then thins again. The changes are slow. They feel like breathing without a strict rhythm. The closing payoff is calm and complete. Giant convection cells are not a side effect. They are a main mechanism that links interior heat to surface texture and to the first steps of mass loss. The next section moves from these surface motions to the gentle heaving layers that help material rise and cool. A slow swell moves through the outer layers of a red supergiant and leaves a gentle trace in its light. The atmosphere rises and settles in long pulses that lift gas into cooler heights. Mass loss begins with lifting rather than with escape. In the primary scene, the disk holds a dim rim that thickens for a while, and then thins again. A faint darker band forms nearer the centre, and drifts outward across the glowing face. It fades as it reaches the edge where the boundary is a gradient rather than a line. That gradient shows how the visible surface blends into a layered atmosphere. The drifting band is not a crack. It is a denser layer that travels through thinner gas and then relaxes. Pulsation is the first core concept, and it stays. Pulsation is a slow expansion and contraction of outer layers. It is a response to changing balance between pressure and gravity in a vast envelope. An everyday analogy can stay simple and natural. On an open sea, a long swell lifts the surface without breaking. The water rises. It levels off and sinks again as the swell passes. A swell carries motion more than it carries water. In a red supergiant, a pulse carries momentum through gas that is already close to floating. The lifted gas expands. Expansion cools it. Cooling reshapes how light escapes and how matter holds together. The lifted layer does not rise as a rigid shell. It stretches and curls at the edges. One side can lift higher while another lags behind. That uneven lift leaves a faint tilt in the halo. A slow gradient appears from centre to limb because the line of sight crosses different heights. In that region, light behaves as if it comes from a stack of semi-transparent layers. Another visual anchor forms above the limb. A thin haze brightens on one side as it rises. It dims as it settles and spreads like mist that thickens when the air cools. Opacity is the second core concept, and it stays. Opacity is how strongly material blocks light. When opacity increases, light spends longer trying to escape. Smoke looks darker when it is thick. Fog looks brighter when it is thin and sunlit. In a red supergiant, small temperature shifts can change opacity strongly. A lifted layer cools and becomes more blocking. The surface can dim even during expansion because the escaping light is filtered through cooler gas. The pulse then slows because trapped heat builds pressure behind the opaque layer. The layer lifts a little farther. It then relaxes as light leaks out again. A long cycle emerges from that feedback without needing a perfect clock. A pulse also changes speed as it climbs outward. Deeper layers are denser and resist motion. Higher layers are thinner and respond more easily. The result can be a steepening front in the outer gas. Many red supergiants show pulsation timescales of about 400 days, like a year that runs long. That single number sets the pace of change at the surface and in the halo. A wave that would cross a small object in minutes can take days to influence an envelope this large. Time stretches when distance grows. The primary scene returns in motion. The darker band becomes slightly sharper for a while. It then softens into the surrounding glow. A curved edge appears within it where brightness changes abruptly over a short distance. That edge is a physical detail. It marks a compression where gas is briefly denser than its surroundings. A shock is the third core concept, and it stays. A shock is a sharp compression that heats gas suddenly. A fast gust can pile air into a thin front. A rolling storm can hide a narrow wall where conditions change quickly. Even mild shocks can push gas higher than a gentle swell alone. They can also create dense pockets where cooling proceeds faster. In those pockets, atoms collide more often and stick more easily. Another visual anchor settles into place. Just above the disk, a scalloped halo shows small arcs and dim gaps. Some arcs look like partial rings that wraps around the star for a short distance. Each arc is a shell that is denser than the gas around it. The shell expands. It thins as it spreads across a larger volume. After a time, it becomes difficult to separate from the background glow. Another scene appears in the outer haze. A small knot brightens and then smears into a thin streamer. The streamer curves gently as it moves outward. Its leading edge is slightly brighter because density is higher there. Now the limit of observation arrives softly and precisely. The main limitation is that depth and motion are mixed together in the signal. A signal would encode motion as tiny shifts in wavelength and subtle changes in line shape. In a thick atmosphere, many layers contribute at once. A rising layer can sit in front of a sinking layer along the same line of sight. The combined pattern can mimic a slower motion than any single layer truly has. Models can separate these effects, yet the separation is never perfect. This is a limit of inference rather than a lack of sharpness alone. The uncertainty is also about separating pulsation from convection. Both processes can shift brightness and apparent motion. Only long tracking of repeated phases can distinguish a cycle from drifting cells. Repeated behavior becomes valuable because repetition constrains what the layers can be doing. When the halo brightens at a similar phase again and again, the cause is likely a real cycle. When the surface pattern changes without repeating convection is likely sharing control. A scale shift widens the view. Seconds describe how quickly light crosses a small space. Days describe how long a pulse can take to reshape a stellar atmosphere. Years describe how repeated pulses build a history in the surrounding haze. The halo's not a smooth sphere. It shows gradients and arcs. Thin clumps drift outward. Pulsation and shocks do not guarantee escape, yet they supply the lift that makes escape possible later. The closing image steadies the tone. The scalloped halo relaxes into a wider, softer glow. The darker band dissolves into the disk. The next section follows the lifted layers outward toward the first grains where light begins to push more effectively. A red supergiant's light softens as if a thin veil slowly thickens in its outer air. Dust begins to form where lifted gas cools enough for solids to appear, and that dust helps turn surface unrest into an outward wind. The first image is quiet and close. The star's limb looks slightly more blurred than before. A faint halo surrounds the disk with a gentle gradient. The halo is not uniform. It has mottled brightness that drifts without hurry. The first unlock arrives early. The blur can be a sign that tiny grains are starting to share the space with gas. Those grains do not glow on their own. They reveal themselves by how they scatter and absorb light. Dust is the first core concept, and it stays. Dust is solid grains suspended in gas. The grains are made when atoms stick and grow in cool, dense pockets. A simple definition can hold. Condensation is gas turning into solid as it cools. Two calm examples place the idea in everyday nature. In a cold cloud, ice crystals appear where air becomes saturated. On a still night, dew forms when air cools below a threshold. Why it matters becomes the next unlock. A red supergiant is so extended that lifted gas can reach cooler regions without needing extreme speed. Cooling becomes possible at heights that are still close to the star in a cosmic sense. The primary visual anchor steadies into a single scene. A pale amber collar of haze surrounds the star. The collar has a sharper inner edge and a fading outer tail. The inner edge looks like a soft boundary where the halo brightens suddenly. The tail thins into darkness with a long, smooth gradient. That shape is a physical detail. It suggests a region where dust forms more readily. It also suggests that the outflow changes character across a narrow zone. At this distance, light behaves as if it is filtered through countless tiny prisms. Some wavelengths slip through, others are dimmed more strongly. The second core concept enters and stays. Scattering is light redirected by particles. Small grains tend to scatter shorter wavelengths more effectively. The star's glow can look redder as the halo thickens. The next unlock follows. A redder tint does not require a hotter core. It can come from cooler dust and from selective filtering at the edge. A slow visual anchor returns within the anchor scene. The collar is not perfectly smooth. It shows faint patches that brighten and fade. Those patches drift outward and spread. They resemble soft puffs that lose contrast as they expand. The motion is gentle. It hints at a wind that is not fully steady yet. The main number can enter safely. Dust formation often begins at about 3 stellar radii, like the third ripple ring spreading on a quiet pond. That scale shift lands without strain. The surface itself is vast. Yet the critical dust zone can sit only a few radii away. In ordinary settings, condensation happens in a thin boundary layer. Here the boundary layer spans distances larger than many planetary systems. The star's outer gas is lifted by convection and pulsation. Some parcels rise higher than others. In those lifted pockets, density stays high enough for collisions to occur often. Cooling then favours sticking. The grains begin as tiny seeds. They grow by collecting atoms and small molecules. The process is slow by everyday standards. It is still fast compared to the star's long life. Another payoff arrives. Dust does not need to fill the whole halo at once. A small amount in the right place can change how light couples to the outflow. The third core concept enters and stays. Radiation pressure is the push of light on matter. When photons are absorbed or scattered, momentum is transferred. Gas alone often interacts weakly with the star's light at these cool temperatures. Dust grains interact far more strongly. The grains behave like small targets that catch passing light and feel a gentle outward push. The push is not violent, it is persistent. It is present as long as the star shines through the dusty zone. The outflow gains traction. The grains collide with gas and share their momentum. The gas begins to drift outward with them. Another visual anchor appears as a slow change in the halo. The sharper inner edge of the collar becomes slightly farther from the disk. The outer tail grows broader. The gradient becomes more extended. The unlock sits inside that widening. Once dust forms, the outward motion can sustain itself more easily. Dust is both a product and a driver. It forms because gas cools. It drives because light can push on it. The wind is born as a partnership between grain and gas. A limit of observation arrives softly and clearly. The main limitation is that grain properties are inferred rather than directly seen. The size and composition of grains affect colour and scattering. Different combinations can produce similar dimming. A signal would mix contributions from many radii along one line of sight. That blending hides the exact altitude where grains first appear. Models use the changing spectrum and the halo brightness to estimate where dust forms. The estimates are meaningful. They still carry uncertainty because multiple grain mixtures can mimic each other. That limit does not weaken the story. It clarifies what is solid and what is tentative. The robust point remains. A dusty zone exists. It changes with time, is linked to the star's surface motion. Another payoff follows from that clarity. If dust formation is patchy, then the wind begins patchy. An uneven collar implies uneven lifting. Uneven lifting implies a wind that starts stronger in some directions than others. The halo's mottling becomes a map of where the star is shedding itself most efficiently. The analogy stays unique and natural. In a mountain cloud, snow begins in colder pockets first. The snowfall then spreads as more of the cloud cools. The cloud does not turn to snow everywhere at once. The same logic scales upward. Dust begins in favoured pockets. It spreads as conditions repeat and overlap. The final scale shift widens the view in time. Minutes and hours govern the flicker of surface patches. Months and years govern the growth and dispersal of a dusty collar. Thousands of years can build layers of dust farther out that record many cycles of lifting and drift. The closing image remains gentle. The amber collar holds steady for a while. It then becomes slightly thinner. The inner edge softens and the outer tail fades into darkness. The next section follows how light-driven pushing and patchy dust combine into a structured wind that carries mass away without urgency. A red supergiant's wind carries away matter so gently that the loss can look like a soft blur around the star. Dusty winds emerge when light steadily nudges dust grains, and the grains pull gas along, creating an outflow that is structured and uneven. The first scene is a wide one. A faint envelope surrounds the star like a thin shawl of dim glow. The envelope is not smooth. It shows arcs that curve partway around. It shows gaps where the glow is weaker. Along one side, a thicker band forms a crescent. The crescent has a sharper inner edge and a fading outer gradient. That physical detail matters. A sharper inner edge suggests a region where density rises quickly. A fading outer gradient suggests expansion and thinning. The first unlock arrives early. A wind can look calm because its speed is modest, yet it can still carry large mass over long time. The second unlock follows soon after. The wind is not a single sheet moving outward. It is a patchwork made by patchy dust formation and by uneven lifting from below. The first core concept is radiative driving, and it stays. Radiative driving is outward push from light on dust. The push comes from many photons transferring momentum. The dust grains act as the main coupling point. They absorb and scatter light and feel a steady outward force. The gas alone does not catch light as efficiently in these cool layers. The grains do. 2 everyday images keep the idea grounded, without bringing in a human world. Pollen can drift when a warm breeze catches it. Fine ash can be carried when it is light and dry. The difference in the star's case is scale and persistence. The push is present as long as light shines through the dusty zone. The grains collide with gas and share their motion. A small payoff follows. The gas does not need its own direct push from light. It needs the grains to act as handles. The primary visual anchor returns again and holds. The crescent band thickens into a partial shell. The shell is brighter on one side and dimmer on the other. It resembles a slow wavefront frozen in haze. At this distance, light behaves as if it grazes a layered fog. Brightness is higher where the line of sight passes through more dust. Brightness is lower where the dust is thinner or absent. The second core concept enters and stays. Clumping is matter, gathering into denser knots. Clumps form because the wind is not perfectly uniform. Some regions begin with more dust, some begin with less. When dust is more abundant, light pushes more effectively. That part of the wind accelerates a little more. It becomes slightly less dense as it stretches. Nearby a region with less dust is pushed less. It can remain denser for longer. That contrast makes the envelope uneven. The next payoff arrives. Uneven push can create structure even in a calm flow. The wind can imprint rings and arcs without requiring a violent event. Another visual anchor appears within the same wide scene. A thin arc splits into 2 parallel strands. Between them, a dim lane opens like a seam in fog. The lane is a real density gap. It grows as expansion spreads matter outward and the strands move apart. The halo becomes a record of different flow histories. Some strands are older and more spread. Some are younger and tighter. A single number can set a clear pace without rushing. A typical wind speed is of about 20 kilometers per second, like a fast storm front crossing a landscape. That everyday comparison stays gentle. It also supports a scale shift. At that speed, a flow travels a huge distance in a year. Yet the star itself is enormous. The wind needs time to build an extended envelope. Days describe shifting patches at the surface. Months and years describe how arcs and shells move outward and thin. Thousands of years can place older shells far beyond the bright halo where they become too faint to track. Another unlock follows from the number. Slow does not mean weak. Over long time, even a modest speed can carry matter far away and clear a wide region around the star. The third core concept enters and stays. Optical depth is how much a path through dust dims light. When optical depth is low, light passes with little change. When optical depth is higher, light is softened and reddened. The crescent band has higher optical depth than the gap beside it. That is why it appears as a thicker glow. This concept can be held by a natural analogy. A thin mist dims distant mountains slightly. A thicker fog hides them almost completely. In the circumstellar envelope, the same logic applies, only the scales change. Another payoff arrives. The same dust that feels the push also controls what can be seen. The wind both moves matter and hides the details of its own launch. Now the limit of observation arrives softly and clearly. The main limitation is projection and degeneracy. A bright arc can mean a dense shell. It can also mean a longer path length through dust at a particular angle. A signal would blend depth into a flat picture. Without true three-dimensional information, shell thickness and location must be inferred. Another limitation follows. Grain size affects scattering and colour. Different grain sizes can mimic similar brightness patterns. Models can narrow the options. They cannot remove all ambiguity. The conclusion remains stable even with those limits. The envelope is structured. The wind is patchy. Dust participates in both. Another visual anchor settles closer to the star. The crescent band casts a subtle shadow on the inner halo. The shadow is not a sharp line. It is a gentle dimming that follows the band's curve. That dimming is a physical detail that reveals geometry. Where dust is thicker, less light reaches behind it. The halo becomes layered in brightness. The wind is revealed as a three-dimensional object even when depth cannot be measured directly. Another payoff follows. Shadows in the halo indicate that dust does not fill space evenly. That uneven filling supports the idea of clumps and arcs. It also supports the idea of a wind that begins in favoured directions. The analogy remains unique and calm. A river in flood can deposit silt and curved bars along its banks. The deposits can form arcs and gaps as the flow shifts. The flow is continuous. The pattern is uneven. In the star's wind, the deposits are not on a bank. They are in space itself, carried outward and spread into shells. A final scale shift widens the view to the star's future without opening new mystery. The outer envelope grows as a quiet memory of many cycles. Each arc records a period of stronger dust formation. Each gap records a period of weaker coupling. Over time, the envelope becomes the environment that later events must cross. The closing image stays gentle. The crescent shell thins. Its inner edge softens. The outer gradient merges with darkness. The next section moves deeper into how magnetic fields and surface patterns can help organize such patchy outflow without breaking the calm. A faint order can appear inside the messy glow of a red supergiant's outer layers. Magnetic fields help organize parts of the surface and the wind guiding where dust and gas gather and where they thin. The first scene is slow and wide. Across the star's disk, a chain of dim patches forms a gentle curve. The curve is not a crack. It is a lane where brightness stays lower than the surroundings, for longer than drift alone would suggest. Above that lane, the halo is slightly thicker. It carries a darker crescent shadow behind it. That shadow is soft. It follows the curve like a shallow groove carved into light. The first unlock arrives early. A persistent lane implies a structure that resists rapid mixing. That structure can be magnetic. The second unlock follows soon after. Even a modest magnetic field can matter in a gas that is thin and weakly held by gravity. Magnetic field is the first core concept and it stays. Magnetic field is a region where charged particles feel a force. In hot, ionized gas particles carry electric charge. They respond to magnetic forces and can be guided along field lines. Two natural analogies keep the idea gentle and unique. In a polar aurora, charged particles follow invisible paths and create arcs. In lightning, a channel forms where electric conditions guide a discharge. The red supergiant's case is calmer than either. It is a slow influence rather than a sudden event. The field does not need to be strong to shape motion. It needs to be present where gas is partly ionized. The next payoff arrives. The field can gather gas into lanes and patches by resisting flow across it more than flow along it. The result is a surface pattern that can persist longer than convection alone would keep. Another visual anchor appears within the main scene. The dim lane shows a slightly sharper inner edge. The edge looks like a boundary where brightness changes over a short distance. That boundary is a physical detail. It hints at a change in temperature or density. It can also hint at a change in opacity caused by a different mixture of gas and molecules. The star's atmosphere is not a single layer. It is a stack of shells with gradients in temperature. Those gradients allow some regions to be more ionized than others. In that region, light behaves as if it's filtered through uneven curtains. Some curtains are thin, some are thick. The field can help decide where those curtains gather. The second core concept enters and stays. Ionization is atoms losing electrons and becoming charged. Even a small fraction of ionized particles can tie the gas to the magnetic field. A short definition holds. Ionization is atoms becoming charged by losing electrons. Two examples return it to plain language. A hot flame can make a gas conduct more easily. A thundercloud can separate charge and make air behave differently. Why it matters follows as a quiet unlock. When gas is more ionized, it couples better to the field. Where coupling is stronger, motion across the field is slowed. Gas can be guided into elongated structures. Those structures can become seeds for density differences in the wind. A visual anchor settles above the limb. The halo shows a long streamer that arcs outward from the dim lane. The streamer is not a jet. It is a region where dust and gas are slightly denser. It catches and scatters more light. It casts a faint shadow behind it. The streamer widens as it moves outward. Its inner boundary is sharper than its outer boundary. That boundary detail hints at compression on one side and expansion on the other. The main number can now enter and remain safe. Surface fields can be about 1 Gauss, like the strength of a small fridge magnet. That everyday comparison stays simple. The scale shift arrives softly. A fridge magnet is small. Here the field is spread over a surface larger than the orbit of inner worlds. The field's strength is not the whole story. Its reach is vast. Its influence is applied over immense areas for long times. Another payoff follows. A weak field can still shape a large wind because the wind is also weakly bound. Small forces integrated over long distances can change paths. In the dusty zone grains form in cool, dense pockets. If magnetically guided flows create pockets, dust begins there first. Dust then makes radiative driving more effective. The field can become an indirect sculptor of mass loss. Another visual anchor appears closer to the star. The dim lane breaks into a chain of spots. Each spot is slightly darker at its center, with a softer rim. The rim suggests a temperature gradient. The center suggests higher opacity from cooler gas. The chain persists as the surrounding mottling changes. That persistence is another unlock. Convection alone tends to rearrange patterns quickly. A field can anchor patterns by resisting some motions and favoring others. Now the limit of observation arrives softly and precisely. The main limitation is that magnetic structure is not directly seen in simple brightness. A signal would show brightness patterns and spectral line changes. Those can be caused by temperature, by motion, or by magnetic effects. Separating them requires models and assumptions. The inference is indirect. A persistent lane could be magnetic. It could also be a long-lived convective feature. The uncertainty comes from degeneracy. Different causes can produce similar surface maps. The limitation is not only resolution, it is also the need to disentangle overlapping effects along the line of sight. That limit guides a careful conclusion. The safe point remains. Magnetic fields can add coherence to patchy lifting. They can help align streamers and shape where the wind is denser. Another payoff follows from that care. Even if the exact geometry is uncertain, the envelope's arcs and shadows imply real structure and density. Something must be organizing that structure. Magnetic guidance is one plausible organizer in a partly ionized flow. The unique analogy can now deepen without repeating earlier images. In a flowing river, a submerged ridge can steer currents into persistent channels. The ridge is not visible from above at first glance. The channel pattern reveals it over time. In the star's outflow, the ridge is magnetic. The channel is a streamer of denser gas and dust. Time makes the hidden structure legible. A final scale shift widens the view toward the future without sharpness. Days describe changes in surface patches. Years describe the growth of streamers into extended arcs. Centuries describe how many such arcs layer into a complex circumstellar environment. The closing image remains gentle. The long streamer thins, its shadow fades into the halo's gradient. The dim lane on the disk softens as convection rearranges the surface again. The next section moves from organized lanes and streamers to the deeper interior clock that continues to change beneath this slow outer motion. Beneath the slow skin of a red supergiant, the interior keeps a quieter architecture that the surface only hints at. The star's core evolves into nested, burning shells, and that layered structure sets the long road toward collapse. The first image is not a diagram. It is a calm cross-section, imagined as if the star were translucent. Deep inside a bright central region sits like a compact ember. Around it lie several broad layers, each with a different texture. One layer is smoother, Another looks mottled as if stirred. Another shows a thin boundary where conditions change quickly. Those boundaries are physical details. They are gradients in temperature and density. They separate zones that behave differently. The first unlock arrives early. The outer surface can look slow because the outer layers are huge. The core can still change in meaningful ways beneath that calm. The second unlock follows soon after. The core does not burn one fuel forever. It steps through zonskis, and each stage leaves an ash that becomes the next core. Shell burning is the first core concept, and it stays. Shell burning is fusion in a layer around a core. A short definition can hold. Fusion is light nuclei joining and releasing energy. Two plain examples keep the meaning grounded in nature. A warm spring can have layers where temperature changes with depth. A lake can have a sharp boundary where water above and below mix poorly. Why it matters becomes the next unlock. In a red supergiant, each burning stage can move outward into a shell. The interior becomes an onion-like structure without needing a sharp solid boundary. One shell burns helium into carbon and oxygen. A later shell burns carbon into heavier elements. The names are less important than the pattern. The pattern is nested activity. The star carries multiple furnaces at once, each in its own layer. A second visual anchor appears within the imagined cross-section. The boundary between two shells is a thin zone where density rises quickly. It is like a narrow band of compression that separates a hotter interior from a cooler layer above. That narrow band can host strong gradients. Those gradients affect how energy moves. Convection is the second core concept, and it stays. Convection appears not only at the surface, it also just appears in some burning shells where heat production is strong. Rising plumes carry hot ash upward. Cooler material sinks to replace it. The result is mixing. Mixing matters because it changes what fuel is available where. A small payoff follows. The surface cells discussed earlier are an echo of this deeper tendency. The star is a fluid system at many depths. Some layers mix vigorously. Some remain more stable. Another visual anchor arrives slow and concrete. In the shell around the core, a ring of brighter texture looks like a turbulent band. Above it, a darker, smoother layer looks more sure. The contrast is a clue. Not every layer convects at the same time. Some shells are convective because burning is intense. Some layers are radiative because heat flow is gentler. At this distance, light behaves as if it comes only from the surface. The interior must be inferred. The inference comes from models and from the star's overall behaviour. The limit of observation enters softly and clearly. The main limitation is that the shells cannot be directly imaged. A signal would carry only surface brightness and spectral information. The interior structure is reconstructed by theory constrained by global properties such as luminosity and composition. Multiple interior arrangements can produce similar outward light. That degeneracy is a real limit. It means the onion structure is the best supported general picture, not a directly photographed map. The story remains solid because the physics of fusion stages is robust. A payoff follows from that clarity. Even without direct pictures, the layered sequence explains why red supergiants can have long surface calm and deep internal change. A single number can now set a safe timescale. The helium burning phase can last about 1 million years, like a long, slow age, compared to a brief season. That everyday comparison keeps time intuitive. The scale shift lands gently. A surface pattern can change over days and years. A core stage can persist for 1 million years. The outer star can seem timeless on the scale of a single lifetime. The core is still moving forward through a deep calendar. Later burning stages become shorter. Carbon burning is shorter than helium burning. Oxygen and silicon burning are shorter still. The exact durations are not needed here. The point is the trend. As the star builds heavier elements, the clock speeds up. Another visual anchor steadies the mind. The central ember becomes more compact. The shells become thinner. Their boundaries become steeper gradients. The star's interior looks like nested layers that tighten toward the center. The third core concept enters and stays. Degeneracy pressure is support from packed particles. A short definition holds. Degeneracy pressure comes from particles resisting being squeezed into less space. Two examples return it to plain language. In a crowded swarm, movement becomes constrained. In a compressed foam, bubbles push back when squeezed. Why it matters becomes the next unlock. As the core becomes denser, ordinary thermal pressure is not the only support. Degeneracy pressure can contribute. It changes how the core responds to heating and cooling. In some stages, heating does not cause easy expansion. That can make burning more unstable in certain conditions. The instability can create bursts of convection in a shell. Those bursts can change mixing and fuel supply. Another payoff arrives. The future supernova is not decided only at the final moment. It is prepared by how shells build, mix, and tighten over time. The wind and dust outside are one record. The shells inside are another record. One is visible as arcs in the halo. The other is hidden as gradients in density. The unique analogy can now hold the structure without repeating earlier images. A tree builds annual rings. Some rings are thick, some are thin. The pattern records changes over long time. In the star shells are not made of wood. They are made of ash and fuel. Their thickness and boundaries record the interior history. Another scale shift widens the view in space. The surface spans distances so large that a single convection cell can cover a quarter of the disk. The core is small by comparison. Its changes set the pace for the whole star's fate. The difference is like comparing a shoreline to the deep seabed. Both are part of the same ocean. They behave on different timescales. The closing image remains gentle. The imagined cross-section fades back to the real view of the surface. The mottled disk glows softly. The halo drifts outward in arcs. Beneath that slow glow, shells continue their quiet work. The next section follows how the core approaches a limit where adding heat no longer provides lasting support. The center of a red supergiant grows quieter in appearance even as it becomes more extreme in state. The core approaches an iron-rich endpoint where fusion no longer provides net support and gravity begins to win in a new way. The first scene is imagined as a soft interior silhouette. The outer star remains broad and hazy. The core becomes a small, dense region that looks darker not because it is cold but because it is buried. Around it, burning shells flicker in slow bands. One band looks turbulent, another looks smoother. Between them lies a thin boundary where density climbs sharply. That boundary is a physical detail. It is a steep gradient where small changes in radius mean large changes in pressure. The first unlock arrives early. A star shines because it converts mass into energy through fusion, and that conversion has limits. The second unlock follows soon after. When the core builds iron group nuclei, further fusion does not release useful energy. Fusion remains a core concept, but the focus shifts. Fusion releases energy when light nuclei merge into heavier ones up to iron. Past that point, energy must be supplied rather than gained. That statement can stay calm and plain. The core's furnace changes from a source to a sink. Burning shells outside can still produce energy for a time, yet the center is no longer replenishing support from fresh gains. The primary visual anchor becomes a quiet symbol. A thin, dark ring appears in the imagined core like a band of higher density pressing inward. The ring is not a solid wall. It is a layer where particles are packed more tightly than nearby regions. That packing changes how the core responds. Degeneracy pressure returns as the first core concept, and it stays. Degeneracy pressure comes from particles resisting compression. The earlier definition remains consistent without repeating its earlier examples. Here it is felt as stiffness. As the core compresses, particles fill available states. The pressure rises without needing higher temperature. That can keep the core supported for a time. A small payoff follows. Support can come from crowding rather than from heat. That changes what heating can accomplish. Heating usually causes expansion. Expansion usually lowers density. In a strongly degenerate core, adding heat may not cause easy expansion. The core can continue to contract even while it heats. Contraction increases temperature further. The center becomes a feedback that tightens. Another visual anchor arrives slow and concrete. The burning shells outside the core resemble nested, glowing curtains. Each curtain has a thin, bright inner edge where reactions are strongest. Each curtain fades outward with a gradient as fuel thins. Those gradients matter because they show where energy is generated. They also show where neutrinos begin to carry energy away. Neutrino cooling is the second core concept, and its stasis. Neutrinos are particles that pass through matter easily. They can carry energy out of dense, hot regions without much interaction. A short definition holds. Neutrinos are weakly interacting particles that escape dense interiors. Two-plane analogies can keep the idea accessible without pulling in human systems. Heat can leak from deep rock through tiny cracks. Scent can drift out of a dense thicket through small gaps. The match is not exact, the calm point is escape through weak coupling. Why it matters becomes a clear unlock. When neutrino losses rise, the core can cool even while shells burn around it. Cooling reduces pressure support from thermal motion. The core then contracts. Contraction heats it again. Yet the heat is partly carried away by neutrinos. The core runs on a treadmill where contraction feeds losses. A single number can set a safe scale without crowding. The iron core can be about the mass of the sun, like one heavy stone held inside a much larger cloud. That everyday comparison is gentle and keeps the scale grounded. The scale shift lands softly. The outer star spans distances so large that a halo can extend for many stellar radii. The core's key mass is concentrated into a region far smaller than the star's radius. Vast outside, compact inside, time also shifts. The outer surface changes over days and years. The inner core can change significantly over months and then days as it nears the end. Another payoff follows. The surface can remain slow while the core accelerates toward instability. The star's fate is decided deep inside long before the outer haze gives a clear sign. Now the limit of observation arrives softly and precisely. The main limitation is that the core cannot be measured directly. A signal would carry only surface light and spectral lines shaped by the outer layers. The iron core mass and temperature are inferred from models. Those models use assumptions about mixing mass loss and rotation. Different assumptions can yield different core structures while still matching surface behavior. This is a limit of inference. It is not solved by sharper imaging of the surface. The uncertainty is in the hidden interior. Yet the qualitative path remains robust. Fusion support fades at the center once iron dominates. Neutrino losses rise with temperature and density. Contraction becomes harder to halt. Another visual anchor returns to the imagined cross-section. The thin, dark ring in the core tightens. The surrounding shells move inward slightly as the core contracts. The shells do not collapse yet. They adjust to a changing gravitational field. The boundaries between shells sharpen because gradients steepen. The star becomes more layered in the interior. Another payoff arrives. Steeper gradients mean more stored potential for sudden change later, even if the surface stays calm. The unique analogy can now hold the feeling of a limit without repeating earlier comparisons. A sand pile can stand quietly as grains settle into a stable slope. Adding grains slowly can make the pile steeper. The surface still looks calm. A small region inside becomes too steep and shifts. In the core, the slope is pressure support against gravity. The pile reaches a point where the center cannot hold its own weight by fusion gains. The approach is gradual. The transition can be swift. A final scale shift widens into the circumstellar environment without opening a new mystery. The dusty arcs outside continue to drift outward at modest speed. They build a layered space around the star. Deep inside the core becomes more compact and more degenerate. The two regions evolve on different clocks. The closing image remains gentle. The surface disk glows with slow mottling. The halo shows a faint crescent and a soft shadow. Beneath it all, the core tightens toward a point where collapse becomes the simplest path. The next section follows how an invisible flow of neutrinos and the rising speed of late-burning stages compress the timeline even further. The last phase of a red supergiant's life is marked by a strange mismatch between what can be seen and what is already underway. Neutrinos begin to dominate the core's cooling, and the final burning stages compress time until weeks can matter. The first image is still the same star from afar. The disk remains softly mottled. The halo still shows faint arcs and a gentle gradient. Nothing on the surface needs to look urgent. Beneath that calm, the core becomes a bright furnace in a different sense. It becomes bright in neutrinos rather than in light. The first unlock arrives early. A core can lose energy rapidly without brightening the surface because the energy can leave as particles that barely interact. The second unlock follows soon after. As neutrino losses rise, the core must contract to maintain pressure. Contraction then heats the core and accelerates new burning stages. Neutrinos are the first core concept and they stay. Neutrinos are weakly interacting particles that escape dense interiors. In that region, light behaves as if it is trapped, while neutrinos behave as if space is almost empty. Two natural analogies keep the idea quiet and unique. Heat can seep through porous stone while water above remains still. A scent can drift through a dense thicket even when air seems calm in open ground. The match is not exact. The useful point is the escape through weak coupling. Why it matters becomes the next unlock. If neutrinos carry energy away faster than photons can, then cooling does not wait for the surface. The core's thermostat changes. The core loses energy. It contracts. The contraction raises temperature and density. Those conditions raise neutrino production even more. The core enters a feedback where contraction and neutrino loss reinforce each other. Another visual anchor appears as an imagined interior silhouette. The central region looks like a small bright knot, not in light but in an invisible flux. Around it, shells glow in nested bands where fusion continues. The boundaries between shells are sharp gradients. They look like thin rings in the cross-section. Each ring marks a place where temperature and density change quickly with radius. Those rings are physical details. They matter because steep gradients make shells sensitive. A small change in the core can shift a shell's strength. Shell burning is the second core concept and it stays. Shell burning is fusion in a layer around a core. The shells move to heavier fuels as the center evolves. The exact names are less important than the consequence. Later, fuels yield less time. The star's internal calendar accelerates. A small payoff follows. The star can spend long ages in earlier stages and then rush through the final ones. The surface remains slow because the outer layers are huge and respond sluggishly. The core is compact and responds quickly. The primary number can enter as a safe anchor. The final silicon burning stage can last about 1 day, like a brief storm compared to a long season. That comparison stays calm and keeps time intuitive. The scale shift lands softly. Days describe a surface pattern drifting and reshaping. 1 day can also describe the last internal stew before collapse. The same duration carries radically different meaning depending on depth. Another visual anchor returns to the outer view to keep the tone grounded. The halo shows an arc that slowly expands. The arc's inner edge is slightly sharper than its outer edge. The outer edge fades into a long gradient. That asymmetry remains a physical detail. It suggests the arc is thinning as it expands. The arc records mass loss from earlier cycles, not the final day itself. Another payoff arrives. The circumstellar envelope is a long memory. It does not update in real time with the core's final sprint. It is built from years and centuries of gentle shedding. Now the limit of observation enters softly and precisely. The main limitation is that neutrinos from such a distant star are nearly impossible to detect in ordinary circumstances. A signal would have to carry an enormous number of neutrinos and be caught with rare alignment and sensitivity. Without that, the core's neutrino cooling is inferred rather than measured directly. The surface does not reveal neutrino flux clearly. Models connect neutrino physics to burning rates. Those models depend on uncertain details such as mixing and mass loss history. This is a limit of direct detection and a limit of inference. It means the timeline of the final stages is guided by theory. It is still grounded in well-tested physics of dense matter. Another payoff follows from that clear boundary. Even with uncertainty and exact timing, the direction is stable. Neutrino cooling speeds up the end. The final stages become short. The core becomes more compact and more unstable. Another visual anchor appears in the imagined cross-section. The central knot tightens. The surrounding shells become thinner. Their inner edges brighten in the sense of stronger burning, then fade as fuel is consumed. Between shells, a narrow region looks smoother. It is a zone where heat is carried outward without strong mixing. The boundaries shift as the core contracts. The entire interior looks like nested layers sliding inward. Another payoff arrives. Sliding boundaries mean changing conditions for convection. Some shells churn strongly, others calm down. That affects mixing and the distribution of elements. It also affects how the star is prepared for collapse. The unique analogy can now hold the feeling of compressed time without repeating earlier images. A long candle can burn steadily for hours. Near the end, the last segment can soften and slump quickly. The light above can look similar. The structure near the base changes fast. In the star, the base is the core. The outer light is the surface glow. The changes in support and in cooling. The acceleration is real, even if the surface looks familiar. Another scale shift widens the view in both space and time. The halo expands at a modest speed and takes years to move far. The core changes in days at the end. The star's life has millions of years behind it. Its last internal steps can fit into a short span of time. The outer star is a vast cushion. It damps immediate surface response. That damping is why the surface can remain calm. Another visual anchor returns to the halo to settle the tone. The arc becomes thinner. Its shadow becomes harder to see. The gradient becomes smoother as dust spreads. The core beneath continues its invisible cooling and contraction. The closing lines remain gentle. The outer wind and dust continue to drift without hurry. Deep inside, neutrinos carry away energy more efficiently than light can. The next section follows how this tightened core reaches a point where collapse begins and a shock must pass outward through the star's layered interior. The moment of collapse begins in silence deep under the red supergiant's calm surface. The iron core loses its ability to resist gravity, and a shock is born when the collapse halts and rebounds at high density. The first image is an interior one imagined with softness. The core is a compact sphere surrounded by thin, burning shells. Each shell has a sharper inner boundary and a smoother outer gradient. The boundaries look like faint rings in a cross-section. Those rings are physical details. They mark where density and temperature change steeply with radius. The first unlock arrives early. Collapse is not a slow dimming of the surface. It is a rapid inward motion of the core that the surface cannot respond to in time. The second unlock follows soon after. A shock forms because the collapsing core does not fall forever. It reaches a density where matter becomes very stiff and the inward motion is abruptly slowed. Core collapse is the first core concept and it stays. Core collapse is rapid inward fall of the central core. It begins when pressure support can no longer match gravity. In a red supergiant, the core is built largely from iron group nuclei. Fusion no longer supplies net energy. Neutrino cooling removes energy efficiently, pressure declines. Gravity tightens its hold. A calm everyday analogy can be unique and natural. A snow cornice can hang in balance for a long time. The snow compacts slowly and the edge looks unchanged. A small internal shift can make the cornice suddenly give way. The surface is quiet until the motion begins. In the core, the balance is pressure against gravity. The shift is a loss of support. The fall begins and accelerates. Another visual anchor appears as an imagined inward ripple. The inner rings of the burning shells draw closer together. Their gradients steepen. The core boundary becomes sharper. It looks like a tight edge where density rises quickly. That edge moves inward as the core contracts. A small payoff follows. Steeper gradients mean the interior can change dramatically, even if the outer star remains broad and slow. The collapse continues until the inner core becomes stiff. The second core concept enters and stays. Nuclear density is the packed state of matter in atomic nuclei. A short definition holds. Nuclear density is matter packed like nuclei with little empty space. Two examples return it to plain language. Wet clay resists compression more than dry sand. Solid ice resists compression more than loose snow. Why it matters becomes the next unlock. When the inner core reaches nuclear density, it stiffens sharply. The inward motion slows. The core can bounce. The bounce sends a pressure wave outward, so that wave steepens into a shock. Shock is the third core concept, and it stays. A shock is a sharp compression front that heats and accelerates matter. The shock is not a visible flash at the surface yet. It is a moving boundary deep inside. Another visual anchor steadies as the shock forms. A thin, bright ring appears at the boundary between the rebounding inner core and the still-infalling outer core. The ring is a physical detail. It is a narrow zone where density and temperature jump abruptly. Inside the ring, matter is compressed and briefly heated. Outside it, matter is still falling inward. The ring expands outward through layers like a ripple moving through stacked fog. At this distance, light behaves as if the star is unchanged. The core event is hidden. The only fast messenger is neutrinos. Neutrinos stream outward in enormous numbers. They carry energy away. They also interact weakly with matter behind the shock. Some of that interaction can deposit energy and help the shock survive. A small payoff follows. The shock is not guaranteed to keep moving outward on its own. It can stall because it loses energy while breaking apart heavy nuclei and pushing through infalling material. Neutrino heating can help revive it. The main number can enter safely in anchor time. The inner collapse and bounce unfold in about 1 second like a single heartbeat compared to the star's long, slow breathing. The scale shift lands gently. The surface convective patterns change over days and years. The core changes in a second. The mismatch is enormous. Another visual anchor appears farther out in the imagined interior. The shock ring moves into the next shell. The shell boundary is a steep gradient. The shock steepens further as it crosses that gradient. The ring becomes slightly jagged. It develops small corrugations. Those corrugations are physical details of instability. They show that the shock is not a perfect sphere. It interacts with uneven density and with turbulent flows in the shells. Another payoff arrives. The interior is already structured by shells and gradients. The shock inherits that structure. The shock's path is shaped by what the star has built over millions of years. Now the limit of observation arrives softly and clearly. The main limitation is that the collapse and shock cannot be seen directly in light. A signal would show only the surface until the shock reaches the outer layers. The timing of shock formation is inferred from models and from rare neutrino detections in exceptional cases. For most distant stars, neutrinos are not measured. The inference relies on physics of dense matter and on simulations. Those simulations depend on uncertain details such as rotation and mixing. This is a limit of direct measurement and a limit of model completeness. Yet the central sequence remains robust. Collapse occurs. The core stiffens. A bounce creates a shock. Neutrinos flood outward. Another visual anchor returns to the outer star to keep calm. The halo arcs continue to drift outward. Dust grains continue to scatter light. The surface remains softly mottled. The core is doing something entirely different. Another payoff follows from this juxtaposition. The circumstellar environment is still being built by winds even as the core enters its final second. The outer layers do not know yet. The shell structure that was built by burning stages now becomes the medium the shock must cross. The unique analogy can now connect timescales without repeating earlier ones. A deep earthquake can rupture in seconds. The surface ocean above can still look smooth until waves arrive later. The rupture is hidden. The consequence travels outward. In the star, the rupture is collapse. The wave is the shock. The surface response waits until the shock reaches it. Another scale shift widens the scene in space. The shock starts near the core's tiny radius and must travel through a star that can be enormous. The path is long, the outer envelope is extended and low density. The shock will change character as it climbs. It will accelerate in thinner layers. It will steepen in gradients. It will meet the dusty wind that has been laid out around the star. The closing image remains gentle. The shock ring continues outward through the layered interior. The The halo outside remains quiet and softly structured. The next section follows how the shock moves through the envelope and meets the circumstellar dust, shaping what the explosion will look like once it finally emerges. A shockwave climbs through a red supergiant like a quiet reshaping of layers that were already fragile. As the shock crosses the extended envelope and meets the dusty wind outside, light and matter exchange roles in a slow unfolding that becomes visible at last. The first scene is the star seen in profile as an imagined cutaway without harshness. Deep inside the shock is a thin boundary. It travels outward through shells that become progressively less dense. The boundary is sharper than its surroundings. It is a physical detail. It is a narrow front where pressure, temperature, and velocity jump. The first unlock arrives early. The shock strengthens in the outer envelope because density falls and the wave steepens. The second unlock follows soon after. What becomes visible is not the core event itself. What becomes visible is the shock reaching layers where photons can finally escape more quickly. Shock breakout is the first core concept and it stays. Shock breakout is the moment the shock reaches a transparent enough layer. At that point, trapped radiation leaks outward rapidly. The outer envelope is extended. It is cool and tenuous compared to the core, yet it is still optically thick for much of the journey. A simple everyday analogy can remain unique and gentle. A swell moving under thin ice can be hidden at first. As the ice thins near a warm patch, the swell becomes visible as ripples and cracks. The swell was there all along. Visibility changes when the barrier changes. In the star, the barrier is opacity. Opacity returns as the second core concept and it stays. Opacity is how strongly material blocks light. In the dense interior, opacity is high. Photons diffuse slowly. In the outer envelope, opacity declines as density drops. The shock carries a hot radiation field behind it. That radiation presses outward. It also heats the material it passes. The envelope responds by expanding. Expansion lowers density further. That can lower opacity further. A small payoff follows. The shock is not only a push of matter, it is also a moving curtain of trapped light. The primary visual anchor becomes a single clear scene. The star's limb brightens in a thin ring. The ring is brightest at the edge, not the center. It looks like a pale rim that thickens and then softens. The rim has a sharp inner boundary and a smoother outer gradient. That is a physical detail that matters. A sharp inner boundary suggests a sudden change in where light can escape. The smoother outer gradient suggests scattering and expansion. At this distance, light behaves as if it floods outward, where the path becomes short enough. A signal would rise quickly and then settle as the envelope continues to expand. Another visual anchor appears immediately outside the star. The dusty collar built over years is already present. It forms arcs and clumps. When the breakout light reaches it, the dust responds. Some grains are heated. Some are pushed. Some regions become brighter because they scatter more light. The third core concept enters and stays. Circumstellar interaction is the collision between ejecta and surrounding wind. A short definition holds. Circumstellar interaction is ejecta ploughing into earlier lost material. Two plain examples keep it grounded in nature. A fast wave can crash into a sandbar and pile water upward. A gust can hit a hedge and create a turbulent wake behind it. Why it matters becomes the next unlock. The dusty wind is not empty space. It is material the star already shed. When the shock-driven ejecta meets, that material energy is converted into heat and light. The light can last longer and be shaped by the structure of the wind. Another payoff follows. The pre-existing arcs and clumps can imprint asymmetry on the light without requiring a non-spherical explosion. The environment acts like a patterned screen. Now the main number can enter safely. The shock can take about 1 day to cross the star's outer envelope like a long night passing from dusk to dawn. That comparison stays gentle. The scale shift lands softly. The core collapse happens in a second. The surface brightening can be delayed by a day because the envelope is vast. Distance matters more than drama. Another visual anchor settles on the outer halo. A bright patch appears where a dense arc sits. The patch is not a point. It is a soft knot that spreads along the arc. Its leading edge is slightly sharper than its trailing edge. That shape is a physical detail. It indicates a front of illumination moving across a curved structure. The knot fades as dust heats and then expands. Some dust may evaporate. That reduces scattering in that region. The halo can first brighten and later dim, not because the explosion ends, but because the dust changes state. Another payoff arrives. Dust is both a reflector and a victim. It can briefly amplify brightness and later disappear. The light curve can carry the signature of dust destruction and reformation. Now the limit of observation arrives softly and clearly. The main limitation is confusion of geometry and time. A bright rim can be interpreted as a breakout at the surface. It can also be interpreted as scattering in a nearby dusty shell. A signal would blend direct light and scattered light. Without knowing the exact distribution of dust, it can be hard to separate breakout from early circumstellar reflection. Another limitation follows. The wind is clumpy, clumps cause uneven scattering. That unevenness can mimic intrinsic asymmetry in the explosion. Models can explore scenarios. They cannot uniquely reconstruct every clump from light alone. This is a limit of inversion. It is not solved by simply watching longer. Yet the broad sequence remains stable. The shock reaches a low opacity layer. Radiation escapes. Ejecta expands outward. It interacts with the pre-existing wind. The dusty environment shapes early brightness. Another visual anchor returns to the star's rim to keep calm. The thin, bright ring softens into a broader glow. The disk is no longer a quiet, mottled surface. It becomes a smoother light source as the outer layers are heated. The limb darkening pattern changes. The edge looks less defined. The halo becomes more luminous as scattered light fills it. Another payoff follows. A red supergiant's extended envelope makes the early light a story of layers. The early brightness is not only about energy, it is about where energy can escape and how it is redistributed by dust. The unique analogy can now connect the envelope and the wind without repeating earlier comparisons. A candle behind sheer fabric looks dim and diffuse. If the fabric tears, a sharp, bright slit appears. If a second curtain hangs nearby, it glows as it catches the light. The light source does not need to move. The visible pattern changes as barriers and screens change. In the star, the barrier is the envelope. The screen is the dusty wind. Another scale shift widens the view into the surrounding space. The ejecta begins near the star and moves outward into an environment shaped over centuries. The shock breakout is brief. The interaction can last longer. The arcs and shells in the wind become lit and then overtaken. They can be compressed into thinner layers. New gradients and shocks form where the fast flow meets slow material. The closing image remains gentle. The bright rim fades into a broad glow. The halo's arcs become illuminated and then soften again as dust changes. The next section follows how the expanding debris carries new elements outward and how the surrounding wind becomes part of the final visible shape without rushing the tone. The debris from a red supergiant spreads outward into space that is already textured by earlier winds. The expanding flow carries freshly made elements and meets the dusty shells, and the meeting sculpts both light and matter into layered shapes. The first image is a wide one. The star is no longer a mottled disk. It becomes a glowing source with a soft edge. Around it, the old dusty arcs remain as pale rings. A new faster front appears inside those rings. It is faint at first. It looks like a smooth bubble of expanding gas. Its leading edge is sharper than the haze behind it. That sharp edge is a physical detail. It is a density jump where the expanding material compresses what it meets. The first unlock arrives early. The explosion does not expand into emptiness. It expands into the star's own past. The second unlock follows soon after. The brightness and shape depend as much on the surrounding wind as on the energy of the blast. Ejecta is the first core concept, and it stays. Ejecta is the material thrown outward by the explosion. A short definition holds. Ejecta is expelled stellar matter. moving outward after collapse. The ejector begins hot and dense. It expands and cools. As it cools, it can form new molecules and later new dust. It also carries layers that reflect the star's onion-like interior. Some layers are richer in oxygen, some are richer in silicon and iron. The exact labels are less important than the idea of stratification. Stratification is the second core concept, and it stays. Stratification is matter arranged in layers by composition and density. Two plain analogies keep it grounded in nature without repeating earlier ones. In a river delta, heavier grains settle closer and finer grains drift farther. In a cooling lava flow, a denser crust can form while lighter froth remains above. Why it matters becomes the next unlock. Layered ejecta can create layered emission. When different layers are heated and shocked, different parts of the spectrum can brighten. The structure also matters for mixing. Instabilities can wrinkle the interfaces. That wrinkling can bring inner material outward. Another payoff follows. The chemical story in the light is a story of layers being revealed and stirred. The primary visual anchor becomes a single clear scene in the circumstellar space. A bright arc in the old dusty shell is struck by the expanding front. The arc brightens along a narrow segment. The bright segment has a sharp leading edge and a trailing glow that fades as a gradient. That edge is a physical detail. It is the place where the new flow compresses the old shell. Behind it, material heats and then cools. The shell's arc is not uniform. It has clumps. The clumps brighten first because they are denser. The bright segment spreads along the arc like a slow ignition line without flame. At this distance, light behaves as if it is redirected by dust. Some light is direct from heated gas, some is scattered by grains. The scattering makes halos and softens edges. The third core concept enters and stays. Dust scattering is light bouncing off grains and changing direction. A short definition holds. Scattering is light redirected by small particles without being fully absorbed. Two examples return it to plain language. Sunlight can glow in a dusty canyon at dusk. A fog bank can turn a distant lamp into a broad halo. Why it matters becomes the next unlock. Dust can make the explosion look larger than the heated gas alone. It can also hide deeper layers by absorbing and re-emitting energy at longer wavelengths. Another payoff follows. The same dust that once traced the wind now becomes a lens and a veil. A single number can anchor the pace without crowding. The expanding front can move at about 10,000 kilometers per second, like lightning crossing a sky, compared to a drifting cloud. That comparison stays simple and calm, and the scale shift lands gently. The old wind shells take years to travel across their own thickness. The new front crosses the same distance in days. Time compression is felt as overtaking. The fast meets the slow. A visual anchor returns to the expanding bubble. Its leading edge becomes rippled. Small corrugations appear along the front. Those corrugations are physical details of instability. They form where a light, fast fluid pushes into a heavier, slower one. Fingers of material can grow, they can mix layers. The mixing is not complete, it is patchy. It depends on local density. Another payoff arrives. Patchy mixing explains why some elements appear early in spectra and others appear later. The star's layered interior is not erased instantly. It is gradually stirred into a more complex pattern. Now the limit of observation arrives softly and clearly. The main limitation is that composition is inferred from spectral features, and those features depend on temperature and density. A signal would show lines that can strengthen or weaken for reasons unrelated to abundance. Ionization changes can mimic abundance changes. Dust absorption can hide some regions. Scattering can add light from elsewhere. This is a limit of interpretation. Without full three-dimensional information, the exact distribution of elements cannot be uniquely reconstructed. Models can propose layered and mixed structures. Multiple arrangements can fit the same light curve and spectra, yet the broad picture remains stable. The ejector carries newly made elements outward. It collides with older wind material. The interaction compresses and heats matter. Dust scatters and absorbs, reshaping the visible glow. Another visual anchor settles on the old dusty arcs farther out. Some arcs remain dim because the front has not reached them. They sit like pale rings with smooth gradients. Others brighten where the front arrives. The contrast creates a layered map of time. The arcs mark older mass loss episodes. The brightened segments mark the present meeting point. Another payoff follows. The circumstellar shells act like timestamps. The distance from the star roughly indicates when that material was shed, even if the exact timing is uncertain. The unique analogy can now connect overtaking and layering without repeating earlier images. A fast tide can run into a line of seaweed left by an earlier calmer current. The seaweed does not move as fast. It gathers and folds as the tide pushes through. The pattern on the surface shows where past flows left traces and where the new flow presses now. In the star space, the seaweed is dust and gas in shells. The tide is the expanding ejector. Another scale shift widens the view to long time. In days to months, the front races outward and the light evolves quickly. In years, the remnant expands into a larger bubble. In thousands of years, the remnant becomes a diffuse structure where the sharp edges smooth into gradients. The closing image remains gentle. The bright segment on the dusty arc fades as the shock passes. The expanding bubble continues outward. Its ripples soften. The surrounding shells remain as faint rings, some newly compressed into thinner layers. The next section follows how over longer time dust can reform in the cooling debris and how the remnant's layered structure gradually relaxes into a quieter shape. After the first bright days, the supernova light begins to change character as the debris cools and thins. Dust can reform inside the expanding ejector, and that new dust reshapes what the escaping light looks like. The first scene is a wide view of the remnant as a soft bubble. The outer edge stays brighter and slightly sharper. The interior becomes more mottled as density drops. Thin filaments appear like pale threads. Darker lanes form where material is denser. Those lanes are physical details. They mark gradients where light is absorbed and scattered more strongly. The first unlock arrives early. Dust does not only exist before the explosion. Dust can also grow again inside the cooling debris. The second unlock follows soon after. The light that remains is powered by an internal heat source that fades with time. Dust condensation is the first core concept and it stays. Dust condensation is grains assembling from gas as it cools. A short definition holds. Condensation is gas becoming solids when temperature and density allow. Two examples keep it quiet and natural. Water vapor can turn into frost on a cold stone. Mist can bead into droplets along a leaf edge. Why it matters becomes the next unlock. When grains form, they block and redirect light. They also radiate energy at longer wavelengths. The remnant can dim invisible light while staying luminous in deeper infrared glow. Another visual anchor appears close in. A thin shell of ejector shows a rippled surface. The ripples look like shallow waves frozen in place. Along some ripples, the brightness drops into a narrow, shadowed groove. The groove is a physical detail. It suggests a denser ribbon where fresh grains gather. A small payoff follows. Grain growth prefers dense pockets because collisions happen more often there. Clumps become nurseries for dust. Smooth regions form fewer grains. The debris is not uniform. It is a patchwork of densities and temperatures. Radioactive decay is the second core concept and it stays. Radioactive decay is unstable nuclei changing and releasing energy. A short definition holds. Decay is nuclei transforming and releasing heat through particles and photons. Two examples keep the idea grounded without human frames. A warm ember cools but still glows from within for a while. A cooling lava crust can stay warm beneath a darker surface. Why it matters becomes the next unlock. The expanding ejector cools by doing work and by radiating. Decay supplies fresh heat from inside. That heat keeps some regions warm enough to glow. It can also delay full condensation in hotter zones. The balance between cooling and heating shapes where dust forms first. A visual anchor returns to the bubble's interior. Several bright knots sit inside the shell. Each knot has a sharp leading edge and a softer trailing gradient. The sharp edge is a physical detail. It hints at a compression, where a slower inner flow catches up. The gradient hints at cooling behind that compression. Those knots can become sites of dust formation later. Another payoff arrives. The same clumps that brighten early can later become darker as grains grow and absorb light. The remnant can appear to turn itself inside out in brightness pattern. Bright becomes dim. Dim becomes bright where infrared emission dominates. The main number can enter safely and gently. Over about 1 year, like a full cycle of seasons on a temperate world's decay, heating fades noticeably and dust signatures can strengthen. That comparison keeps time intuitive. The scale shift lands softly. The explosion begins with seconds and days. The dust story unfolds over months and years. The outer wind shells took centuries to build. The remnant now crosses those earlier layers on a slower clock than the first shock. Another visual anchor shifts outward. A faint ring in the old circumstellar dust becomes compressed into a thinner arc. The arc has a sharper inner boundary and a smoother outer halo. That boundary is a physical detail. It shows where the expanding debris pushes into older material. The push can create a reverse shock that travels inward through the ejector. Reverse shock is the third core concept, and it stays. A reverse shock is a compression wave moving back into expanding debris. A short definition holds. A reverse shock is a shock driven inward by interaction with surrounding gas. 2 examples keep it natural and distinct. A wave can reflect off a cliff and return across a lake. A gust can hit a dense grove and send turbulence back downwind. Why it matters becomes the next unlock. A reverse shock reheats inner layers and can destroy fragile grains in some zones. It can also compress other zones and help grains grow in shielded clumps. The remnant becomes a contest between formation and destruction. Another payoff follows. Dust is not a single event. It is a repeating process across zones with different histories. Some clumps grow grains and darken. Other regions are reheated and remain bright and dust poor. The overall appearance becomes more structured with time, not less. Now the limit of observation arrives softly and clearly. The main limitation is that dust amount and dust temperature can mimic each other in light curves. A warmer small mass can glow like a cooler larger mass at certain wavelengths. Clumping adds another ambiguity. A signal would average over many sight lines. Dense clumps can hide large dust masses while revealing only their outer skins. Scattering further complicates the picture by redirecting light from other directions. This is a limit of inference from integrated light. It cannot be fully solved without spatial resolution that is often unavailable. Yet the qualitative pattern remains stable. Cooling allows grains to grow in dense pockets. Decay heat fades with time. Interaction drives shocks that reshape the distribution. Another visual anchor settles on a single clump. The clump's near side shows a faint bright rim. Its far side fades into a shadowed tail. The rim and tail are physical details. The rim suggests illumination and heating at the surface. The tail suggests absorption and a cooler interior. The clump slowly expands and thins. Its dust becomes more transparent at longer wavelengths. Another payoff arrives. Shadows are not only absence, shadows are evidence of dust. They mark where grains have formed enough to block light. The remnant becomes a map of hidden material drawn by its own illumination. The unique analogy can now hold the overall transformation without repeating earlier ones. A glassy pond can freeze from the edges inward on a still night. The surface looks smooth at first. Then faint patterns appear beneath as frost crystals branch and thicken. Some patches stay clear where water is moving. Other patches turn opaque where growth is favoured. In the remnant, the frost is dust. The branching patterns are filaments and clumps. The clear patches are hotter zones kept dust poor by shocks and decay heat. Another scale shift widens to cosmic time without sharpening the tone. The grains formed here drift outward with the remnant. Over thousands of years they can mix into a wider medium. Over far longer spans they can become part of future clouds and future worlds. The closing image remains gentle. The bubble continues expanding. Dark lanes deepen in some regions and fade in others. The light slowly shifts toward longer wavelengths as grains and cooling take over. The next section follows the remnant as it relaxes into a larger, quieter structure that carries the star's elements outward across long time. As the glare softens, the remnant begins to look less like an event and more like a structure. The expanding shell slows, the interior becomes filamentary, and the star's last winds remain as faint rings that guide the final shape. The first scene is quiet and wide. A pale bubble fills the region. The outer boundary is a thin arc of light with a slightly sharper inner edge. Behind it lies a smoother haze with darker lanes. The lanes are physical details. They trace density gradients where absorption and scattering are stronger. The first unlock arrives early. A supernova remnant is not a simple sphere of expanding gas. It is a layered system shaped by old winds, new shocks and cooling. The second unlock follows soon after. The geometry carries memory. The arcs and filaments are the star's history written into space. Remnant expansion is the first core concept and it stays. Remnant expansion is the outward growth of the debris bubble through surrounding gas. The expansion is fast at first, it gradually slows as more material is swept up. The outer boundary remains the main interface. That boundary is a physical detail. It is a thin shell where density rises and pressure is higher than inside. It can show a sharp brightness rim because emission increases with compression. The primary visual anchor becomes a single steady image. The outer rim is not smooth. It breaks into scallops. Each scallop has a bright crest and a dim trough. The crests connect into a lace of arcs. The troughs open into darker pockets. The lace is a physical detail. It comes from instabilities and from uneven density in the surroundings. The old dusty wind is not uniform. It has shells and clumps. As the expanding front meets those features, the shell bends and wrinkles. A small payoff follows. Wrinkles in the rim reveal density, structure in the environment. The remnant becomes a map of what the star expelled before it died. The second core concept enters and stays. Shock heating is gas heating when a shock compresses it. A short definition holds. Shock heating is rapid warming when a compression front passes through gas. Two examples return it to plain language. A wave breaking on a shore churns and warms the foam slightly. A sudden squeeze of air in a narrow gap can feel warmer than the surrounding flow. Why it matters becomes the next unlock. Shock heating powers much of the remnant's glow long after the initial flash fades. It lights up thin shells and filaments. It also changes chemistry by breaking molecules and later allowing new ones to form as the gas cools. Another visual anchor moves inward. Inside the rim, filaments stretch like threads. Some are straight, some curve into loops. Many have a bright spine with a softer halo. The spine is a physical detail. It marks a narrow region of higher density or stronger magnetic alignment. The loops can arise where flows shear and roll. The filaments can also trace where clumps are being shredded into ribbons. Another payoff arrives. Filaments are not decoration. They are evidence of mixing and compression. They show where energy is dissipated into heat. They show where the remnant is turning motion into structure. Radiative cooling is the third core concept and it stays. Radiative cooling is loss of energy by emitting light. A short definition holds. Radiative cooling is gas losing heat by emitting photons. Two examples keep it calm and distinct. A hot stone cools faster when it glows faintly at night. A warm mist cools as it radiates into a clear sky and thins. Why it matters becomes the next unlock. Cooling can make shocks thinner and shells denser. When gas cools, pressure drops. The shell can compress into a narrower layer. That can sharpen the rim and deepen the dark lanes behind it. Cooling also allows dust and molecules to survive in shielded clumps. The remnant becomes a balance of heating at the shock and cooling behind it. The main number can anchor the timescale. After about 1,000 years, like a long history compared to a brief storm, a remnant can be many light years across, and its expansion can be noticeably slowed by a swept-up material. The comparison stays gentle. The scale shift lands softly. The earliest moments are seconds and days. The remnant phase is centuries and millennia. The star's pre-explosion wind shells can sit at distances built over centuries. Now the remnant expands into that archive. Another visual anchor settles on a faint outer ring beyond the main rim. The ring is dim and smooth. It has a sharp inner boundary and a broader outer halo. The boundary is a physical detail. It can be a compressed wind shell that is only now being reached by the expanding front. The ring brightens unevenly where it is denser. The unevenness makes the remnant appear lopsided, even if the explosion energy is fairly symmetric. Another payoff follows. The surrounding wind can dominate the apparent shape. Dense arcs brighten and become visible. Sparse regions stay faint. The remnant's outline becomes a conversation between expansion and environment. Now the limit of observation arrives softly and clearly. The main limitation is projection. A three-dimensional shell is seen as a two-dimensional image. Filaments that look connected can be separate along the line of sight. Bright rims can be edges of a shell or overlaps of multiple layers. A signal would integrate emission through depth. Without full velocity information, different geometries can look similar. Another limitation follows. Dust can obscure inner regions and hide cold, dense gas. The inferred mass and energy depend on assumed filling factors and on uncertain clumping. This is a limit of reconstruction. Yet the broad physics remains. Expansion sweeps up material. Shocks heat and compress. Cooling densifies shells, filaments form from instabilities and mixing. Another visual anchor returns to the interior for calm closure. The center is not empty. It holds a faint glow with soft gradients. Darker lanes cross it like gentle shadows. Bright knots appear where clumps are compressed. The knots are small and slow-changing on human timescales, but they evolve on the remnant's clock. Another payoff arrives. The remnant is a continuing process. It does not end when the light curve fades. It keeps redistributing elements, shaping dust and preparing material for future clouds. The unique analogy can now hold the remnant's long, quiet evolution without repeating earlier ones. A river after a flood leaves braided channels across a plain. The water level falls. The channels remain as ridges and troughs. Later flows follow the paths of least resistance. The pattern is a memory of the flood and a guide for what comes next. In the remnant, the flood is the explosion. The braided channels are shells and filaments. The future flows are later shocks and the gentle mixing into surrounding space. Another scale shift widens to deep time. Over tens of thousands of years, the remnant fades and merges with the wider medium. Its sharp rims soften into gradients. Its filaments disperse. Its dust and elements become part of larger clouds. The closing image remains gentle. The lace-like rim continues to expand and dim. The faint outer rings persist like quiet echoes of older winds. The next section resolves the journey with a soft perspective on how red supergiants seed space with structure and materials, then lets the narrative settle into rest. The final light of a red supergiant story is often quiet, carried in thin shells that fade into the wider dark. The lasting result is a dispersed mixture of gas and dust that joins larger clouds and changes what can form later. The first scene is a wide, calm view of a remnant near the end of its sharp phase. The bright rim is now faint. The boundary is still visible as a soft arc with a slightly sharper inner edge. Inside, the glow is uneven. Wisps of emission form a loose web. Dark lanes lie between them. Those lanes are physical details. They mark denser strands where scattering and absorption remain stronger. The first small unlock arrives early. The remnant is not simply fading, it is mixing. The second unlock follows soon after. Mixing spreads the star's elements into a volume far larger than the original star. Mixing is the first core concept, and it stays. Mixing is the blending of different gases through turbulence and shear. A short definition holds. Mixing is different materials becoming interwoven until differences are hard to separate. Two examples keep it grounded. A warm and cool current in the ocean can braid and blur into one. A patch of fog can stretch into filaments and vanish into clearer air. Why it matters becomes the next unlock. Mixing is how the star's heavy elements leave a recognizable shell and become part of a larger medium. Without mixing, the material remains locked in a compact structure. With mixing, it becomes available to future clouds across a wider region. A second visual anchor moves in close to a filament. The filament is thin and slightly curved. One side has a brighter spine, the other side fades into a softer halo. The spine and halo are physical details. They show a gradient in density and temperature. The filament frays at its ends into smaller threads. Those threads drift outward. Another payoff follows. Filaments are the intermediate stage between a coherent shell and a fully blended medium. They are the remnant's handwriting as it is slowly erased. Elemental enrichment is the second core concept, and it stays. Elemental enrichment is the addition of heavier elements to surrounding gas. A short definition holds. Enrichment is raising the fraction of heavy elements in a region. Two examples keep it gentle. A river can carry fine silt that makes distant water more opaque. A volcanic plume can spread ash that changes the reflectivity of snowfields. Why it matters becomes the next unlock. Heavy elements alter cooling and chemistry. They allow gas to radiate energy more efficiently. They allow more complex molecules to form in colder zones. They also provide solid materials for dust grains. A visual anchor settles on the remnant's outer boundary where it meets older wind material. The boundary is now broader than before. Instead of a sharp rim, the edge becomes a gradient from bright to dim. The gradient is a physical detail. It suggests that the shock is weaker and spread across a thicker region. Behind that edge, a faint arc appears like a ghost ring from an earlier wind shell. The ring is incomplete. It is brighter in one quadrant where material is denser. Another small unlock arrives. Old wind shells do not disappear. They become templates that guide late-time structure. Dense arcs slow the flow. Sparse sectors let it expand more freely. The remnant's final shape becomes an imprint of its pre-explosion history. The main number anchors the long clock. Over about 10,000 years, like a quiet span compared with a brief storm, many remnants disperse enough that their rims become difficult to trace as distinct arcs. That comparison keeps time intuitive. The scale shift lands softly. The explosion begins on the scale of seconds and days. Dust and cooling patterns unfold over years. The merging into the wider medium takes millennia. The star's earlier winds build shells over centuries. Now all of those timescales overlap in the fading structure. Dust survival becomes the third core concept, and it stays. Dust survival is where the grains persist through shocks and mixing. A short definition holds. Dust survival is grains remaining solid instead of being broken or vaporized. Two examples keep it natural. Ice crystals can persist in shaded pockets even as nearby air warms. A delicate sand ripple can survive gentle breezes but vanish in stronger gusts. Why it matters becomes the next unlock. If grains survive, they carry elements in solid form into future clouds. If grains are destroyed, those elements return to gas and follow different chemical paths. Both routes matter. They change how quickly material can cool. They change what molecules can form. Another visual anchor shifts to the remnant interior where clumps persist. Each clump has a bright rim and a darker core. The rim and core are physical details. The rim suggests ongoing heating at the surface. The core suggests shielding and colder conditions. The clumps slowly expand, their contrast softens with time. Another payoff follows. Shielded clumps can be the last refuges for molecules and dust. They act as small reservoirs that release material gradually as they dissolve. Now the limit of observation arrives softly and clearly. The main limitation is that the true distribution is three-dimensional, while the signal is a projection. Brightness depends on density and temperature along the line of sight. Different mixtures can produce similar light. Clumping adds uncertainty because small dense knots can dominate emission, while hiding most of the mass. Another limitation follows. The inferred element amounts depend on assumed conditions. If a temperature is slightly different, the same emission can imply a different mass. This is a limit of model inversion, yet the qualitative outcome remains stable. The remnant spreads material outward. It becomes less distinct. It becomes part of a larger cycle. A unique analogy can hold the final dispersal without repeating earlier ones. A seed head can release a cloud of fine filaments into a gentle breeze. At first, the filaments cluster and drift together. Then they separate into a wider field. Some settle quickly, some remain suspended and travel farther. In the remnant, the filaments are enriched gas and dust. The breeze is turbulence and large-scale flow. The settling is cooling and incorporation into denser regions. A final visual anchor widens to the calmest view. The rim is now a faint suggestion, not a boundary. The interior web is thinner and more transparent. Dark lanes soften into gentle gradients. Light behaves as a quiet tracer of where energy still dissipates. A signal would show more glow where gas is still compressed. Elsewhere, the remnant blends into the background. The last payoff arrives and resolves the arc. The red supergiant's convection winds and dust do not end as a dramatic finale. They end as distribution. The star's materials become part of the larger medium. Over long time, that medium forms new clouds with slightly altered chemistry and cooling. The closing sentences remain gentle. The remnant continues to expand and relax. The last sharp edges soften into gradients. The region becomes quiet again, carrying a faint and enduring change.